Throughout this course, we will see three different types of approaches of analysis of differential equations. A scientist, engineer, or mathematician would often spend many years of his or her life trying to find the solution of a differential equation. This quest for solutions is called the analytical approach. Once they are realized that explicit solutions are at best difficult to obtain and at worst impossible to obtain, mathematicians learned that a differential equation itself could be a fount of valuable information of the qualitative features of solution. Such an approach is called qualitative analysis. Finally, sometime a differential equation cannot be solved by analytical methods, yet it can be proved that a solution exists. Then the next logical query comes to our mind is, can somehow the values of the unknown solution be approximated? This query takes us to the realm of numerical analysis. Direction fields are valuable tools in studying the solutions of differential equations of the form y prime equals f of x comma y, where x is the independent variable and y is the dependent variable, and f is some function of x and y. Direction fields are also known as slope fields or tangent fields. A direction field for equations of the form above can be constructed by evaluating the function f at each point of a rectangular grid of points in the xy plane. A direction field drawn on a fairly fine grid gives a good picture of the overall behavior of solutions of a differential equation. Usually, a grid consisting of a few hundred points is sufficient. The construction of a direction field is often a useful first step in the investigation of a differential equation. Let's see how to produce the direction field of the equation y prime equals x plus y. Let's try to produce the direction field for the equation y prime equals x plus y, where f of xy equals x plus y. We first take a point P in this rectangular grid. The slope of the tangent line to the unknown solution at P is given by the right hand side of this equation. Since geometrically y prime gives us the value of m, slope of the tangent line to the unknown solution, which is given by the formula x plus y. So for example, at P, the m value of the tangent line would be 1 plus 1, which is 2, which is shown here. Similarly, if we change the point, for example, at 2, 0, we get 2. At 3, 0, we get 3. At some other point, with these coordinates, we get the corresponding m value, which is changing from point to point. Let's try to draw the tangent line there with the given m value. So the m value at P with coordinates 1, 1 is 2. Now if we draw a tiny line segment centered at P, and if we do the same for so many points and try to fill the entire space, 2D space, with these tiny line segments, we obtain a picture like this. This field of tiny line segments is called a direction field, also called a tangent field. So this tangent line is the tangent to the point P of the equation, the unknown solution. Now we might ask, if we have a point A and somewhere on this plane, does the differential equation have any solution passing through this point A? And we see, yes, there is a solution following the direction and passing through the point A. And we can ask the same questions for a different A. And we see, whenever we choose an A, we get a solution of this differential equation following the direction of the field. So this direction field is suggesting the appearance or shape of a family of solution curves of the differential equation. As we see that the m value of the tangent line to the unknown solution is changing from point to point, we might ask whether there is a series of points where the m value remain constant. And this can be simply obtained by the differential equation itself. Since the y prime is exactly the m, so if we remain this constant, then x plus y would be a constant. For example, we might ask, what are the series of points where the m value is 1? So if we connect all the points where the m value remains 1, is this straight line. For example, if we choose a point P and we see that m value is 1 there. This series of points is called an isocline of the differential equation.